Welcome to our lecture number 1 in the engineering drawing 2. We want to discuss about development of lateral surfaces of simple solids. For example, this is a rectangular object that can be wrapped with the plain paper, of which one would unfold. From the wrapped paper, when unfolded, it will look like this. So this one surface that have been unfolded. This is the top part of it, and this is the bottom of it. And the two here, the two sides that have been unfolded here and here. So this is how one can have the development of the lateral surfaces for a simple solid object. For example, here we are having a cube. This cube is of the side of 40 millimeters long. So drawing this, the development of the surfaces for the cube can be done this way. First of all, you need to draw the front part of it, one side to be the front, like this one here. It's the front of this cube, and this is the plan of our cube. So, or top view. So for development, this is one face for the front, this is for the top view, and the remaining 4 are the sides for the cube. So this is the development for our given cube of 40 millimeters long. And now let's see the development of a cylindrical body. You are taught to draw the development of a cylinder of 40 millimeters diameter and 60 millimeters high. You have to draw the front of the given cylinder, followed by a plan of it, and from this plan you have to divide the plan into 12 equal parts. As you can see here, they are labeled 1 up to 12. These divisions are labeled 1 up to 12. From these divisions, you have to project the lines vertically from the plan to the front view. And the other thing which is very, very important to note is to get the total length for our development. Mind you, the height for our development is given is 60 millimeters high. So this is our height here. So with the height or altitude, no problem. But the length for our development, we need to determine it through the formula that is pi d. Pi d, that means you have to use the given diameter and the pi to get the total length, which is the perimeter for our cylindrical body. So this is the length from 0 to 12 is the length for our development, which is due to the perimeter of our cylindrical body or given cylinder with the given diameter. So the other part is the top part of it here, the cover at the top and another cover at the bottom. However, it's not of our interest for the moment. We only want to focus on the lateral surfaces. So have a look for development of a prism. So a prism, as we have said, it is given an example of a plain paper that has been wrapped to the surfaces, then unfolding it, you come to have the sides like A, B, C, D, and F. So after you have unfolded, that plain paper will look like this one. A, B, C, D, E, and F. F and E is the top and bottom part of our cylinder, but the lateral sides are A, B, C, and D. So let's see for the problem number 1 of the square prism. You are told to draw the development of the lateral surfaces of a right square prism of edge of the base 30 millimeters and axis of 50 millimeters long. How to go? Let's see. So from the given problem, first of all, you draw the front of our given prism to the dimensions provided. We know that our plan here, top view, is 30 to 30 because it's a square. It's a square prism. It's a square prism. So this side and this one, they are equal. So 30 millimeters long. From the top, you can see like this. But from the front view, you can see our prism to this height of 50 millimeters long. But in order to get the total length for our perimeter, we have to multiply the 4 sides that form our prism. The prism have got 4 sides. Therefore, it is a matter of multiplying 30 times 4, you get 120 millimeters long. This is our total distance, total length for our developed surfaces. 1, 2, 3, 4 lateral surfaces for a given prism. Let's see how we can develop a cylindrical object. As you have said for the previous case, that we take an example of wrapping around this cylindrical body a plain paper, of which when we unfold it, it looks like this. So this is the lateral surfaces for our cylinder, and the top part of it is here, and the bottom part is somewhere here. For the case of the development of a complete surface of a cylindrical drum being the case, and the diameter of 40 millimeters and the height of 60 millimeters long, let's see how one can accomplish this. So first of all, you need to draw the plan or top view of our drum, followed by the front view of our drum. Then from the plan that has been drawn, you need to divide it into let's say 8 equal parts. 8 equal parts, and these 8 equal parts are labeled A, B, C, D, E, F, G, and H. As you can see here, they are labeled. From these points that are labeled from our plan, they are projected upwards. They are projected upwards to the front view of our drum. However, in order to obtain the total length for our drum, developed surfaces for a drum, we need to apply our formula, that is pi d, or 2 pi r, having the diameter which is 40 millimeters long, so it becomes easier for our case to simply multiply this one pi d. So the total length becomes 125.6 millimeters long. Having aware that the divisions that we have in our plan is 8 from A to B. This arc here, approximation method, the arc from A to B is regarded to be A to B, capital letters A to B. How many are they? They are 8. 1, 2, 3, 4, 5, 6, 7, 8. So it is A to A. A total length being 125.6 millimeters long. So this is our development. Mind you, the height that was provided is A to P, which is 60 millimeters long. So this is our developed surfaces for our drum. See another problem for hexagon prism with the edge of base 20 millimeters long and axis 50 millimeters long. This axis rests with its base on horizontal plane such that one of its rectangular faces is parallel to the vertical plane. It is cut by a plane perpendicular to vertical plane, inclined at 45 to the horizontal plane, and passing through the right corner of the top face of the prism. So you are told to draw the top view first, then draw the lateral surfaces for the truncated prism. Truncated prism means a prism that has been cut and the truncation line is inclined at 45 degrees to the horizontal plane. How to go? Let's see here. So first of all, as I've said, you need to draw this hexagon. Hexagon is prism is drawn here with the side of 20 millimeters and followed by drawing the front view of our prism correctly here. Is drawn correctly in totality with the construction line. Then from our top right corner, at the top right corner, this edge is touched and ensuring our truncation line forms 45 degrees with our axis, or 45 degrees with the horizontal plane here. You can see horizontal plane here or here is 45 degrees. So it's very important here to note that from the top corner, top corner of our prism is where intersection or the line passes through and is forming 45 degrees with the horizontal plane. So having the truncated prism at the points A, the point A which was projected up until it meets the truncation line here, it is indicated or it is labeled by 1 dash. 1 dash you can see here. However, from B and B dash here, you can see B and B dash. The line projected to the truncation line forms number 6 dash, which and 2 dash. So at this point, there are two numbers. It is 2 dash and 6 dash. You can see here. Likewise for C and E, they are in line, so they form at a point. They form 3 points, 3 numbers, which is 3 dash and 5 dash. But at D, the maximum height forms only one number, which is 4 dash. So these numbers are projected to the end view, our case. First of all, you are required to draw a line or the base for our developed surfaces, which ranges how many millimeters. It should be 20 times the number of sides, which is 1, 2, 3, 4, 5, and 6. So 6 times 20, it is 120 millimeters long. So the total length for our developed surfaces is 120 millimeters. So the case is for the height. The height, the lowest point is 1 dash, here, 1 dash. So the folding, unfolding of this is at this point, which is 1 dash unfolding. When you are unfolded, because it will be rotated, it becomes again 1. So from 1, it comes to be 2. Our 2 is here, followed by 3 here, and the maximum number here is 4 here. Again, it goes down, which is in line with 3 is 5. In line with the 2 is 6. Then back to A to point A, which is 1. That's how we can come up to developing the lateral surfaces for a truncated prism. Let's see for a hexagon prism with the side of 20 and a height of 45 millimeters, and is resting on one of its ends on the horizontal plane with the two of its lateral faces parallel to the vertical plane. It is cut by a plane perpendicular to the vertical plane and inclined at 30 degrees to the horizontal plane. The plane meets the axis at the distance of, so this is a point to note. The plane meets the axis at a distance of 20 millimeters above the base. So from the base up to a distance of 20 millimeters through the axis is where the line of truncation is located. So draw the development of the lateral surfaces for the lower part of the prism, and this can be found on the page 300 for our reference book. Let's see. Being the case here, you first draw the plan of it. Our plan being given a side of 20 millimeters long for a hexagon. You know the formula for drawing a hexagon. Then from the top view of our prism, we draw then the front view in totality by construction line you can see here to the height of 45. But one thing to note from our axis is center line here, vertically placed center line at 20 millimeters from the bottom, 20 millimeters from the bottom, from the base of this prism being when standing at 20 is where a line of truncation passes. So it's where you have to lay a line of truncation being how many degrees? 30 degrees from horizontal. 30 degrees from horizontal. So after you have indicated where the points of intersection occur, you need now to project those lines from line of truncation. Then they should be projected to the end view, which would facilitate obtaining the development of our prism. As you can see, as we said for the previous case, that here there are 2 points here, it is 3 and 5 in line. Likewise for this one here is 2 and 6 in line, and 1 is alone here, and 4 also is somewhere there. 4. The lowest point for our case is 4. The highest point is 1, as you can see. Because the unfolding started at 1, it must end at 1 as well. So you can see 1 being the highest point here, likewise here at P is also the highest point. But the total distance to be taken is 6 times 20, as we have elaborated for the previous case. This is how one can come to obtain the developed surfaces for a truncated prism. Another problem 5, it is the case of now a pentagon, prism site 25 and altitude 50 millimeters. Yes, and so a line of truncation where it is 45 degrees to the horizontal, perpendicular to a vertical plane, passing through the center of the axis. Center, you have to note here, center of the axis. So the axis for our prism of a height of 50, so it's going to be where? Let's see. So you can see, after you have drawn the plan or top view of your prism, then you need to construct the front view first. Front view. From your front view, given that you have indicated where is the axis is center line for your case, then you need to locate where is the center of your axis from the bottom, because we have 50, so the center is at 25. So at this very 25, you need to lay the cutting plane being inclined at 45, as you can see here, 45. So this 45 is for the inclination of the cutting plane. So the same procedures will be taken in order to achieve the height for a respective point. As you can see, point A, 1 here, point B, there is 2 here, is alone, it's not in line with another point. When you come to 5, it's also alone here, you can see here. And it's given the hidden line to indicate that you cannot see it clearly from the front view. It is behind. It is laid behind. So 5 is our 5. Cannot see it. Another point is point C. C is 3 and 4. 3 and 4 being at the same point here. Only that the last one here, 3 is alone here, and there is 4 somewhere here. 4 is the highest point here. Then you need to come back at 5. Yeah, 5 is going down, as you can see. 5 is here, and 1 that is going back. Where 1 always the starting point and the ending point, they are of the same level. That's how one can show the development for a truncated pentagon prism. This one is found on the page 15.4 with the altitude of 60 and the base side of the base is 30 millimeters long. So can see on how to go. They resemble very much, but here the axis is 35 millimeters above the base. Yeah. Another problem here. Here is a case of cylinder. Draw the development of a lateral surface of the lower portion of the cylinder of diameter 50 millimeters and axis 70 millimeters when sectioned by a plane inclined at 40 degrees to the horizontal plane and perpendicular to the vertical plane in the bisecting axis. It's very important to note bisecting axis. Let's see, now the thing is done. So the axis always is regarded from the base out to the upper part of the cylinder. So our cylinder plan or top view is given like this, and we have decided to divide it into 8 equal parts, as you can see, 1 up to 8. So there are 8 segments, 8 parts that form this one, 8. These points, they are projected upwards for the purpose of locating where they intersect with the cutting plane. Where this cutting plane is laid, you need to refer the instruction given in our question that the intersection occurs at the center of the axis. So our axis is from here to here. So where it intersects, for sure it is 35 millimeters from the base, because the total height is 70 millimeters. So we expect that it is falling at 35, as you can see, 35 millimeters above the base. And it's being inclined at 40 degrees from horizontal. If it's measured from horizontal plane, it's 40 degrees. So these points, as we have said for the previous cases, we have to project them upwards until when they intersect with the truncation line, cutting plane here. So we will have to extend or project them in this direction to the end view. But one thing very important to note, the total length for our development, that is A to A. How do you get it? You have to remember that we said it is pi d, pi b. The circumference for our case will be regarded as pi d, or 2 pi r. You obtain the total length for our development. So having the total length, you'll be in a position now to indicate the divisions that were found in our front view. But from the given plan, we have 8 parts. So these 8 parts are given here as well for our end view, showing how the cylinder has been developed, a truncated cylinder has been developed. Thank you. Another problem of with the same approach, this one is found on the page 305. Let's see. Yeah. As we said, the case of total length is found by pi d. D is our diameter here. So it's indicated very, very clearly, as you can see, being labeled with the numbers so as to show the corresponding heights. Another example for cylinder is provided here. Draw the lateral development of the solid, having given the diameter as well as the height, and the angle of inclination for the truncation line is 55. So after we have done for prism, let's now see for the pyramid and cone how to go. So here is radial line development method. With this case, development of pyramid, we take the same example of wrapping as a plain paper around this pyramid. So when you happen now to unfold the wrapped paper, what happens? You can see if you unfold it, it looks like this. So we'll have the sides like A, B, C, and D, and the bottom part of it. So in totality, or generally, you will have such kind of development for a prism A, B, C, D, and E for the bottom part of our pyramid. So one can be given a problem like draw the development of the lateral surfaces of a square pyramid, with the side of the base being 25 and height being 50 millimeters long, resting with its base on the horizontal plane and an edge of the base parallel to vertical plane. So here is the pyramid. A pyramid have got our pyramid have got 4 sides. You can see here the square pyramid. A square pyramid. It means that our base AB is 25. Likewise, AD is the same. They are equal. It's the same. So after you have drawn the top view, you draw the front view. Drawing the front view, having given the height for the axis is 50 millimeters long. So the major part or crucial point to note for this case is how to obtain the so-called true length of a slant edge. This line is very, very important in order to have the actual development for a pyramid. You need to draw first the line that is parallel to the line AB, which is one side of our base. So this line being parallel, the line OA1 being parallel to line AB, as you can see here, but followed by drawing an arc with a radius OB. Drawing this radius leads you to obtain a point at A1. This point at A1 gives you another step of drawing this line vertically until when it reaches a bottom line for the base of your front view of your pyramid. So this line here, where it touches a prolonged one or a line that was projected vertically parallel to the line BC parallel, until when it touches the horizontal line for our base of pyramid. So it intersects at A1 dash. At A1 dash is a point where a line, which we term it true length of a slant edge, it goes now to O dash. So this line O dash is a line of our interest. It's a line of our interest because it's the one that will help us to drawing the development for our pyramid. So the line O dash is up to A1 dash, which is now termed a line OA. For our case here is a radius OA. You draw a convenient arc here, but very important thing to note: this how will you get to reach the point B is the distance from A to B is known. You see how much? 25. So this is approximation. It is 25 millimeters long. Likewise for BC, same size, which is 25 millimeters long. Likewise for C, D, and D to A. So they form the developed lateral surfaces for a pyramid. That's how to get. So the very important is to notice here, how do you come to obtain the true length of a slant edge? This slant line is not equal to this one here. It's not actual. So you need to have skills in obtaining this line A1 dash to O dash, which we need to drawing the actual length for our radius, which will facilitate the exercise of developing the lateral surfaces for our pyramid. Let's see for the case of a cone. A cone, also we start wrapping a plain paper around it. When we unfold it, it looks like this. When we unfold the paper wrapped around the cone, so after you have unfolded, it looks like this. So there is a lateral surface and the bottom surface of the cone. Let's see a problem how to go. Conditions. Set that draw the development of the lateral surface of a cone of base 48 millimeter and altitude 55. C. Here is a cone, as we have said. We first of all draw the top view plan, and then you project it upwards, these points A to A dash, C to C dash. So this is the base for our prism. Then knowing that the altitude is provided 55 millimeters long, so we reach somewhere there. Then we note that is A dash, O dash to C dash, back to A dash. So you obtain now the front view of our cone. Our cone is given. In order to achieve the development for our problem, we need to note that in order to achieve the angle for our total development, the angle which will give us the arc length A to A. How do you get the arc length for our problem? You need to use the formula which is radius of the of our cone over the true slant edge times 360 degrees. So from this formula, you can obtain the angle of which will help you to identify the arc length for the total arc length for your development of a cone. So it is 24, given that 24 is our radius for our cone, then dividing by 60, which is the true slant edge for our case. True slant edge for our case. So you need, after you have performed the computation, you obtain the theta, which is a representation of the angle turned, the angle that is forming the total arc length for our development. So it becomes 144 degrees. 144 degrees. This is the case. But remember, we had 4 sides. 1, 2, 3, 4. 4 sides. 4 sides. The 4 sides are to be indicated here. Then you can divide the angle obtained into the number of sides you have. For example, here dividing 144 by 4, you get 36 for each. So 36 here for each division here. But from A to B, how do you get it? Is from approximation of a part of from our top view, A to B. By using your compass, you can take this distance here from A to B. Problem 12. A square pyramid of base side 25 millimeters and altitude 50 millimeters rests on its base on the horizontal plane with the two sides of the base parallel to the vertical plane. This one is cut by a plane bisecting here to note. It is cut by a plane bisecting the axis and inclined 30 degrees to the base. So draw the development of the lateral surfaces of the lower part of the cut pyramid. Have a look here. As we have said, you need to draw the top view of your pyramid. Our pyramid here is 25, 25, 25, 25. So you draw then the front view of it, total, followed by truncating it. How, where, and where to truncate? We are told that at the is bisecting. You have to note this. Bisecting the axis. Axis is regarded from here, bottom, and apex here. Apex here. So if you are told that is bisecting, that means it's making into two equal parts. So from 50, so the equal part will be taken as 25 from the base. 25 millimeters from the base, so it's here. So the angle 30 from horizontal, 30 degrees from horizontal. That's how. Now you obtain the line of truncation here. After you have obtained this line of truncation, as I have said, the very important thing to note is to draw a line which is parallel to the one side of our horizontal until when you get it touching at A1. How do you get it to A1? You have to draw an arc using the radius OB. Drawing this arc here until when it touches this intersect with the line that was drawn horizontally or parallel to AB. Here, as you can see, we get a point A1. So this point A1 is projected vertically parallel to the line here, forming A1 dash. A1 dash is very, very important here for our case because it's where we will draw our true length of the slant edge. So our line of slant edge emerges here up to O dash. This O dash, now we have managed to obtain a true length of our slant edge. So this one we use to draw an arc for our given development, which would be regarded as our radius for OA, AO being our radius. You can draw any convenient arc, only that you have to bear in mind that the sides for our pyramid, each side is given 25. So A to B 25, B to C, C to D, D to A then. Back to A. So the four are provided. When it comes to which length, you have to measure from the apex or with respect height or line being the case, or dash to 4. 4 and 1 are at the same point, as you can see, 4 and 1. So 0 or you'd say O to 1, you mark. Then the rest is A to 1 object line. Also, when you come to O to 2, O to 2 here, the cutoff part, the cut-off part here. Another cut-off part is O to 3, O to 3, cut-off part. Yes, cut-off part here. You can see. How do you get this? You can measure through the lines which are projected to, in order to get the actual length. All these points have been projected. These points are projected horizontally until when they touch is where? The slant line. This is the slant line, the one that we have used to drawing the development here. So you have to transfer these points until when they touch this very line here of our interest. So points 1 and 4, 2 and 3, they are here. So points 1 and 2, 1 and 4, 2 and 3. You can see all the points are here in a line of. So from this line is where now you can copy the respective point, being the case if it is O dash to, or regarded to be O dash to 2 dashes. You can see now, yes, that's how you can obtain these points if you refer to the points marked on the true length of the slant. And we have already elaborated on how one can come to obtain this true length of a slant or edge, which we use to draw an arc, and from this arc we can indicate the respective height for each line, and then we can draw the object lines for each side or each part to indicate the development for entire pyramid. Square pyramid, another problem, base 35 millimeters, side 70. Also this kind of a problem is of the same nature, of course. This can be obtained on the page number 15 on our reference book. One can come to this. Everything has been elaborated as per the previous case. But one thing to note here, how one can come to obtain the true length of the slant edge. See how this has been placed. Yeah, now it becomes true because it is emerging from the edges, as you can see here. Emerges from the edges. So this line here forms the edge here, 70, because as you can see, OA is equal to O dash A dash. A O A is equal to this. Yes, so you can come to that to conclude that when it is drawn, a plan is drawn to this, and this leads to the projection of a front view for our pyramid, results into the true length of a slant edge if it is laid like this in comparison to the previous square pyramid. This is a hexagon. It was a square, now it's a hexagon. Let's see. The only thing here, it is cut by a plane inclined at 40 degrees to the horizontal plane, and they're perpendicular to the vertical plane. The cutting plane bisects the axis. Another point to note, bisects the axis of the pyramid. So you are told to obtain the development of the lateral surfaces for the truncated pyramid. See here. That term bisecting, can you see? Bisecting here, that means 30, because the total is 60, so it bisects the axis. That means it cuts at the center of it. However, you have to remember, is lying at 40 degrees from horizontal. So you can now obtain the line of truncation. After you have obtained the line of truncation, see now what has happened here. Because now we can be in a position to project a line for our true line of slant edge. So the same procedure, you draw an arc. You draw an arc, given that OR is our radius. OR is our radius. We draw until when we touch a line horizontal, a line that is forming horizontal with our case. Horizontal, you can see here, horizontally laid here. With our base here. We've got our base horizontally, and also this one is drawn horizontally until when it touches at A1, where at A1 is where we project a line to touch the horizontal line for our base. For our base. Then from this point we have to project it to O dash. O dash, then this is our line of interest. This is our line of interest because we're going to facilitate on obtaining the arc. So this being given OP, which is equal to O dash A1 dash. Now you can easily locate where is 1, 2, 3, 4, 5, 6, and 1. Where is due to the lines that have been projected, to the line of slant edge here. Slant edge, slant edge, slant edge. Yes, slant edge. So you got all the points here. Points 3, 4, 2, 5, 1, 6. So they are all here. One can come to that then. Yeah. Another problem is about hexagon pyramid. Bisect the axis of the pyramid. So you have to be very careful to understand the requirement of the question. Requirement of the question. Yeah. Radius, true length of the edge. Remember on how we said one can go. So this one has been drawn to the left hand side. It's not a matter. It's not a thing to worry. Instead of drawing them always to the right side of it, it has been drawn to the left of it. Only that the radius is OP, drawn until it reaches P1. The P1 is projected until when it touches the horizontal line for the base, where is P1 dash. So from P1 dash up to O. This O to P1 dash is a line for our true length of a slant edge, of which all the lines from the truncation line have been projected to. You can see the 3 and 4 have been projected until when it intersects or it cuts at a point 3 dash Likewise, for the point 2 dash, 5 dash, it touches a line at 2 dash, and 6 it touches at 1. That's how one can come to produce this development of a pyramid. Yes. Another problem. The same approach you can see here. Same problem here. You simply, first of all, you draw what? You draw your plan. Drawing your plan, then you draw your front view. Maybe something to add here. From the given corners or points that form your pyramid, this is pentagon. For the pentagon pyramid, you need to construct the lines until when they meet at the center. These lines are very, very important here in order to lead you on projecting the points back to the line of truncation. After you have drawn the base of your pyramid, then you need to draw until when they meet at the center from each edge. As you can see, from D to O, E to O, then A to O, B to A, and C to O. These lines will help you to understand how it looks like when it comes for a plan. And these lines, if they are projected, these points here, if they are, have a look here, if a truncation line is somewhere here, after you have drawn it very correctly, you need now to project them back. Here, 5, you can see this 5 here, there is a 5 dash here. 4, there is a 4 dash here. And 3, there is a 3 dash somewhere there. 1, there is 1 dash here. From this 1 dash, you can now project a line that is parallel to the horizontal line until when it meets there, our true length of the slant here. It's very, very important to note here. Likewise for 5 dash until when it reaches 2 dashes, 2 dash, it goes and intersecting where with the true length of the slant. It is tapped now 2 dashes here. Likewise for 3 dash. So these points here on this very line, now are taken to this curve here. Mind you have drawn in totality the arc, the total, a convenient arc, and followed by indicating the divisions A, B, C, D, E, and A, back to A. It's very important regarding the sides that it consists 1, 2, 3, 4, 5 pentagon, 5 sides. Correct. Lastly is the height. How far is from A to 1? How far is A to 1. How did you come to that? Why is 1 here? 1 is here. So you'd have taken this one here from O to 1, followed by O to B, O to B. And this B and 5, they are the same level. So you can see here at 2 and 5, same level from O. And 4, likewise, yeah, it follows 4 here, then 6. So one can obtain this after being measured from the top. Then using the compass, you can mark where it ends. Then you provide the thicker lines or object lines for the partitions that form the total development for our pentagon pyramid. Another pentagon pyramid, which is given there. Where to lay this 25 millimeters above the base, truncation line maybe. Let's see. So from the base, you are told to cut it where at 25 millimeters from the base. Yeah. After you have obtained the true length, how do you obtain? After you have drawn an arc until it touches the horizontal one here, then you project upwards S1 dash, S1 to S1 dash. Then this line from S1 dash, when it reaches O, is a true slant, a true length of the slant edge. True length of the slant edge. The other procedures would be the same. Yeah, a cone. Let's see for a cone now. A cone of the base of diameter 60 millimeters and a height of 70 millimeters long is resting on its base on the horizontal plane. It is cut by a plane perpendicular to the vertical plane and inclined at 30 degrees to the horizontal plane. The plane bisects the axis. The plane bisects the axis of the cone. Draw the development of its lateral surfaces. Yeah, see how to go. Of course, same procedures as done at the previous case. You draw the plan for our cone. Our cone is drawn, then divided into 8 equal parts. Being the case here, we have decided to take 8 instead of 12. It's not a matter. Then these points have been projected. The points D, F, C, G, B, H, and A. They are projected to the front view, where these points, if they are laid to the center or dash, they have to intersect with the line of truncation. If a point is obtained after intersection, you can see this point B and H, they are in line, mind you. A line is projected until when it touches the horizontal for our base. Then this point H now is termed B dash, and H dash is projected up until when it reaches the apex or point O dash. But at this very point of intersection with the truncation line, it obtains, or it forms 2 dash and 8 dash. These 2 points have to be given for our true length. They have to be used for our true length for development here. So you can see at this point we have got 8 and 2. Another point is 7 and 3. Another point is 6 and 4, regarding where they are emerging. If there are 2 in line here, also at the point you need to indicate them. All right. After we have obtained this, we have to remember this is a cone. For a cone, how to determine the total length that will form our development, we need to first of all calculate for the total arc, total angle for our arc, total angle. This angle is obtained by R over L multiplying the ratio by 360 degrees. Then you get the theta. Theta is our interest, the angle turned. The angle turned indicates the distance covered by this development from A to A. So it means that the R is the radius for our diameter, and the height L is for our height of our cone, So it was supposed to be 30 over 70 times 360 degrees. Then you get the total angle 142. This 142 is the theta here. Total angle turned through, that is theta. However, we had 80 segments, 80 parts. So we need to divide this total angle by smaller angles, which is, it becomes 17.8. So each angle, because here you're going to divide them into equal parts, but how do you get this one? Is from the space on our plan. The space on our plan, that is A to B, is capital now A to B. From A to B in smaller letters, now it is in capital letters A to B. But the angle, when you come to the angle, is 17.8, if at all it was correctly computed here. That's how one can come to obtaining this development. 35 was obtained because this, you are told that it is bisecting the axis. So to bisect, that means it cuts at the center. Another problem is for a cone. A cone again, 50 millimeters diameter and 60 height, resting there. Yes. So another thing here to note is passing through a point on the axis at 22 millimeters from the apex, from above, apex from above. Let's see. So from this very point, it goes down through the axis. How much? 22 here. So this line was lying through at this very point. To which angle? Angle given here, the angle given, referring to the angle given for this truncation. So after you have obtained this, you have to use the same procedures. The points obtained through cutting this line will be projected until when they meet this very line of truncation here, which will be now will be projected towards the line of for our true length. But when you draw here, you are told to you are supposed to draw the full development for a cone, then indicating which part was cut. Is how the object line will indicate to differentiate the total and the left. After this one was removed, after cutting, a certain part was removed. This is the one that is left behind here. So these lines indicate where it touches after it has been removed, these points here. So remember to project them at the very center from the divisions points. Then you project them back. As you can see here, line goes to the center here. But this line indicates where it has come to cut this line. Then you project it downwards until it indicates where is the boundary for our curve here. This line is also projected to the outer line here, making 4. Another here is 3 and 4 in this very line, outer line, because this one is a true line for our slant edge here. So we use this line to get the points for our length here, and we should be very careful to note which lines have been cut with this line of truncation. Which one? Other lines are left outside, like HA and AB, they are left outside. So this is how one can come to the development of a truncated cone. Thank you for having me today.